All right, so let's pick up where we left off and use our calculator to get answers to these logarithmic expressions. On your calculator, you're going to push the log button, and remember that means the base is automatically 10. Log of 1 is going to be 0, which makes sense because if I write that as log base 10 of 1, if I'm at 10 and I try to get to 1, obviously the exponent would have to be 0. Let's do log of 100. Log of 100, close parentheses, oops. And that, as we would expect, pops out a 2 because 10 to the second is 100. That makes sense. Same thing with part C. That one will have to approximate because if base is 10, 10 to the what gives me 90? I don't know, something between 1 and 2, I guess. Log base 10 of 90 is going to be 1.95. And now let's go look at ln, where the ln button is. The ln button is right before the log, below the log button. So I push ln and then 1, and we would expect that to also be 0. Since log base e of 1, e to the 0 gives me 1. Again, remember, that just says log base e of 1. ln to you should mean log base e. And if I have e to the 0, I get 1. Let's go look at ln of e. ln of e. So let's make sure you know where the e button is. That's also in the background of the ln button. It's in blue, so to access it, I'm going to push second and then ln, and that's going to give me e to the, I'm going to put an exponent of 1 and then close my parentheses. So that's saying ln of e, and as you might have already guessed, the answer should be 1. Now let's go say I have, this guy is log base e of e. It makes sense that if I'm at e, and I'm trying to get to e, the exponent would have to be 1, because e to the 1 is equal to e. So ln of e being 1 makes sense. Let's go look at ln of 10. We're going to have to approximate that. Looks like it's 2.30. So we have 2.30 for ln of 10. So just know basically where the log and the ln button are on your calculator and how to access them. And they are right underneath each other. Now let's go to example 5, where all we have to do is solve the given equation, which means either guess the base, the argument, the exponent, and I can do that quickly by just applying the circle I told you guys about. So if I put this in exponential form, this equation is essentially saying 2 to the x should give me a half. 2 to the x should give me 1/2. And if you were to guess, what would the exponent need to be to give you a half? 2 to the what gives you a half? It would have to be -1, so that 2 to the -1 makes that reciprocal of 1/2. So all we had to do was basically guess the exponent. Let's do the same, apply the circle to part B. This guy says x to the second should be 25. Well, that's just a quadratic equation. We can solve it and get two values of x. X is equal to plus or minus 5, but the base cannot be negative. So x would have to be just 5. Let's make sure we point that out in the notes too. When we went and put the log form and the exponential form, where did that go? Right here. Remember we said these two guys are equivalent? And in the exponential section notes, we had said that the base a has to be positive. It's never negative, and it's not 1, because if it's 1, it's just going to stay a linear function, flat, and not become exponential. So remember that the base a has to be positive. Okay, let's go back to the example. So the only one I keep is the positive 5. And that makes sense. 5 to the 2 will give me 25. Part C, pause the video and try that on your own, and then come back and check to see if you got the same thing I did. Okay, so if you applied the circle, x to the 3/2 must be 8. And in order to solve this, remember I have to undo the exponent. So I'll go ahead and raise both sides to the 2/3 power to undo that exponent, so that power raised to a power can cancel out, and I can get x to the 1, and I have 8 to the 2/3, which means this is the root and this is the power. So I have a cube root of 8 and the power is 2. So cube root of 8 is 2, and when I square that I get 4. So x equals 4 must be my final answer. That one was a little bit more involved than the other ones. Part D, remember, if you don't like ln, you can always write that as log base e of x equals -1. And if you want, you can apply the circle to it. So now we've got e to the -1 must be x, and I think we're done. We've already solved that for x. So our answer is, I guess, 1 over e, if I take the reciprocal. Okay, next, let's go ahead and look at graphs of logarithms. And we'll start with an exponential function we've seen before and relate it to logarithmic graphs. So we know from before, we did this guy, we graphed it in the previous sections. We said it goes through 0, 1, and it has, as you go to the right, it's got a growth, so you walk up, and it's got that asymptote y equals 0, and we have the domain, which was 0 to infinity, and the range, which was, domain, I meant everything, -infinity to +infinity, and the range was from 0 to infinity. So this we looked at in detail. We graphed it by hand in the previous sections. Now, if I ask you, is this 1-to-1? You would say, well, yeah, because it passes the horizontal line test, which we talked about in the previous chapters. And if it passes the horizontal line test, it has an inverse, right? So if I look at this exponential function and I try to find its inverse, I would say, all right, well, that's equivalent to y equals 2 to the x. And then from the inverse section, we said you would isolate the input or the x and then switch your x and y. So if I do that, if I try to isolate the x here, it's an exponent. If I'm needing access to the exponent, I must be using logarithms. So if I write that as 2 to the x equals y, I can write that as log, the base is 2, the exponent that was spit out is x, and the argument therefore must have been y. So all I did was change it from exponential form to logarithmic form. And now I have step 1 done. I've isolated the input x. X is alone all by itself. Step 2 in finding inverses was switch the roles of x and y. So now I have log base 2 of x equals y, which means my inverse function must be log base 2 of x. So I started with the exponential function. I followed the steps of trying to find an inverse, and it got me to this log function, which means logs and exponentials are inverses of each other. So always remember that. If I give you an exponential function a to the x, whatever the base a is, its inverse will have to be log base a of x. Logs and exponentials are inverses of each other. In other words, if I want to graph log base 2 of x, I could go do it by hand, or I could just do the image across the line y equals x, from the graph of the exponential function that I have. So we'll look at it by just going and inputting some values and then tying it back to the exponential function. So let's make an XY chart. And I'm going to put some values. Let's say I put -4, -2, -1, 0, 1, 2, 4. I'm going to put those and evaluate them quickly. So I picked the negatives on purpose so that you would see 2 cannot get to -4. Remember up above we said the argument can't be negative. There's no exponent that'll make 2 turn into a -4. So this will be undefined. That'll be undefined. That'll be undefined. Remember, logs also can't take inputs of 0. We showed that upstairs. In other words, 2 to the what gives me 0. No exponent will give me that. So the first place where I can actually give an output is right here. I am at 2, and I'm taking log base 2 of 1. And log base 2 of 1, I guess, will have to give me 0, because 2 to the 0 gives me 1. Now log base 2 of 2. 2 to the what gives me 2 itself. The exponent would have to be 1. Log base 2 of 4, because I wanted to input a 4 for my x. 2 to the what gives me 4. It would have to be 2. So if I just go plot these guys, let's see if we get something that might mimic the inverse of the exponential function. So I have 1, 0, 2, 1, and I have 4 and 2. And if I put, like, let's say 1/2, let's put one more. I'm going to get log base 2 of 1/2. And in order to get 2 to become 1/2, remember I need a negative exponent to be spit out. So my next ordered pair is going to be 1/2 for my input of x. And then my output was going to be a -1. So 1/2 gives me -1. Now notice and compare this with the graph of the 2 to the x that I had drawn up here. Do you see how that graph is kind of like this graph if I were to imagine the line y equals x here, what we had talked about in the inverse section of our notes? So my exponential function will actually be here, and its inverse is going to be this g function that we got, which is log base 2 of x. So if you wanted to, you could have just graphed 2 to the x and then switched all those x and y values, and you would get this log function, because logs and exponentials are just inverses. Now, I also want you guys to keep in mind the domain of the log function, the one in red. It only starts here and then you go to the right, so the domain is 0 to infinity. The range, however, the y values go all the way down and slowly up and up and up. So the range is from -infinity to +infinity. And we also have to keep in mind that the log function always has a vertical asymptote at x equals 0. Just like the exponential function had a horizontal asymptote at x equals 0, this guy has a vertical asymptote. So pay attention to 2 to the x, which we graphed in detail before in the previous sections. There was a horizontal asymptote, the domain was -infinity to +infinity, and the range was 0 to infinity. And watch, those things have sort of reversed for this log function. Now I have a vertical asymptote, and my domain and range are switched from what the exponential function domain and range were, if I pay attention. The domain and range automatically switched because they are inverses after all. All right, in the next video, we'll look at different bases and the graphs of logs on your TI. For now, our main goal was to know that logs and exponentials are inverses of each other and what the graph of log base 2 of x looked like.